Hello, welcome back to another lecture on galactic foreground emission mechanisms as a part of the cosmological component separation course. In this lecture we'll be focusing on dust and specifically thermal dust emission. As always, let's refamiliarize ourselves with the microwave foreground gallery. In this lecture we're focused on the red line, which has to do with the thermal dust emission. We can see that the thermal dust emission dominates over other galactic foreground emission mechanisms above 70 gigahertz and is one of the most important of all foregrounds to take into account in CMB analysis. Dust grains are typically about 0.01 to 0.2 micrometers in size and are mainly composed of metals such as carbon, oxygen, magnesium, silicon, and iron. These dust grains will absorb starlight in the UV and optical and re-emit that energy as light in the far infrared and infrared. And dust is typically about 1% of the interstellar medium's mass. There are two main observables when it comes to dust. The first being extinction, which is shown here as compiled by Brandon Hensley and Drain in their 2021 paper. You can see that the total extinction is significantly stronger than the polarized extinction, and that the total extinction has some characteristic lines due to the composition of the dust. Additionally, we also have the thermal dust emission, which is the other main observable. After the dust grains have heated up from absorbing optical and UV light, they re-emit that energy away in the far infrared, as shown in the plot here. As is often the case with CMB science, we're mostly concerned with the polarization. So what is physically happening with dust polarization? Well, first, the grains must be both aspherical and aligned. Spherical grains will not have any net polarization, as there's no preference for which direction the light should be emitted. So we need something more like an American football in shape that is oblate or prolate. It will emit or absorb photons with the E vector along the long axis. But if all of these oblate or prolate grains are randomly oriented, we will get no net polarization. However, dissipative processes will bring the angular momentum vector into alignment with a magnetic field vector, and if there are many grains that are aligned together, we will get a net polarization. The composition of the grains is mostly carbonaceous and silicate in nature. The silicate features indicate robust polarization, and the carbonaceous features unexpectedly features a notable lack of polarization signatures. Both of these have been observed. When it comes to modeling thermal dust emission, there are two big things to consider. How do we parameterize the emission, and how can we make a more physically informed model? So the typical approach for modeling thermal dust emission is to take the total dust intensity as just a product of the amount of dust, the amplitude, the dust composition, which is represented by a power law, frequency scaling, and then the Planck function, which has a characteristic dust temperature. This is the standard for parametric fitting in CMB science, and the real question is it adequate? The Planck data analysis found that a single modified blackbody component did a good job of describing the emission throughout the Planck data. However, Meissner and Finkbeiner, when analyzing the Planck data, found that actually a two-component modified blackbody model fits the data better. There are some things that are of concern here, such as the SED flattening around 1,000 gigahertz. This is something that is difficult to model with a single component sufficiently, but we also have a notable lack of data around 1,000 gigahertz. There are also some noted spatial variance in dust emission, which we'll show now. By looking at the ratio of dust emission at multiple frequencies, we see that the ratio of dust emission at 857 gigahertz over the ratio at 353 gigahertz reveals that there's cooler dust along the galactic plane and hotter dust up at higher latitudes. And as we move up in frequency space, we see that this characteristic is also visible there. We also have to consider SED variations and decorrelation. One of the difficulties with the SED variations is that the dust SED may vary along the line of sight, and probably does, and that the sum of modified black bodies is not a modified black body in itself. This makes modeling more difficult. In polarization, we have to consider decorrelation. Line of sight changes in the magnetic field directions, as shown in this cartoon below, can enhance SED variations, making it more difficult to get a proper full model of the actual emission that we observe. Alright, are we done? Well, no. Nearly, but we still need to consider some more physically motivated models. So let's look at Astrodust, which has been proposed for small scales, and the H1 dust correlations for larger scales. So Astrodust is a model that's been formulated by Brandon Hensley and Drain in the 2020 paper with the goal of trying to fit observable features by modeling the actual dust grains themselves, which these dust grains are thought to be a mix of amorphous silicates and other materials that can be combined into grains that can match both the observed extinction and observed emission. For more details, see the paper. H1 dust correlations, something to look at right away is if you look at just by eye, look at dust intensity at 545 gigahertz as opposed to the hydrogen column density, we can see that the morphology of these two observables are very, very similar. And if we zoom in and bin the data itself, we can see that the emission as a function of hydrogen column density is approximately linear in the low column density regimes. We can attempt to model this emission as a function of hydrogen column density by taking just a nice linear approach here where you have the hydrogen column density, and then for each dust component you have some characteristic dust opacity, and then a dust temperature that corresponds. We can simplify this model into something linear where you have the emission is equal to the dust opacity times some dust to gas ratio times some hydrogen column density, which is then multiplied by the Planck function in a similar manner to the modified black body that we saw earlier. This looks very similar to the model that we had before. The difference is that we aren't assuming any dust or any frequency scaling in this kappa nu, and we are expanding this this amplitude value that we saw earlier to encapsulate the hydrogen column density as well. Summary: there's lots to still learn about what dust is actually made of from the microphysical side of things. CMB experiments are full of dust information, which is both good and bad. It's good for those who are interested in galactic physics, but it's bad for those who want to have a clear view of the CMB. Simple phenomenological models, such as the modified blackbody, do a decent job of cleaning up CMB datasets, but some refinement could help. Thank you very much.